Hi, thank you all for coming. I'm Robin. I'll be talking about tracing, Rust, and scale. There we go. Alright, first a bit about myself. I'm a staff engineer here at KOMOJU. As Richard mentioned, we deal in payment processing, which means reliability is very important to us. And we're mostly a Ruby shop, but we also have some Rust. As mentioned, we also have some Python, we have some Kotlin, we have some Swift for iOS. I'm working in the core platform engineering group, so I'm working on a lot of shared libraries, I'm working on observability, I'm working on all kinds of other things that are less relevant to this talk. And I have been a Rust user since 1.36, so I remember the try micro. This is 2019-ish for context. And yeah, I hope that after this talk tonight, all of you will get kind of an overview of tracing, and you'll learn actually a lot about tracing, and hopefully you can go home and instrument your own Rust applications. So I have three parts in this presentation. We're going to start with some basics, so we're all on the same level in terms of tracing. We'll then dig into a lot of implementation details of specifically tracing. And in that section, we'll jump around a bit, but I promise it makes sense at the end. And then in the last third, we're going to talk about practical solutions, actually instrument your code and get data. This talk's very long. I had to cut a lot of content, so please hold your questions until the end. I numbered the slides so you can refer back to them. I have a link to the slides. The link will show up again in the end as well. So if you want to grab the slides, you can do that. And yeah, let's get into part one. So let's first talk about a bit about tracing. And when I talk about tracing, there's actually several different things you could interpret. So there's a Tokyo tracing library, and there's tracing in the abstract context concept. And I will specifically talk about how to use the tracing library to create tracing like this, so we can introspect our code. So if we start talking about tracing the context, the concept, this is a trace. It's commonly represented like this as a flame chart, which is notably not a flame graph because it has a time axis. And it consists of several spans, which you can see here in different colors. The spans form a tree, and you have a root at the top, and you have several children. And we use color coding in this case to kind of mark different components in the span. So you might see, like, this is Python, and you can see down here, so red is apparently. So the trace overall, you would say it's an operation, an interaction, that's like logically cohesive. And as an example, we often use an HTTP request, but it might also be a message handler from message bus, or whatever operation makes sense in your system. And the trace really only has a trace ID, which is either 64 or 128 bits, depending on your system. And well, then it contains spans. And the spans themselves, again, have span IDs, commonly 64 bits. They belong to the span through, they belong to the trace through the trace ID. And they might have a parent span ID, or they are root span, and that's how we get the actual tree structure within the trace. And technically, you could have several roots within a trace, but that's advanced stuff. And then, so we can lay them out on our time axis somehow. They also have start and end time, or they might have a start duration, depending on the implementation. But most importantly, they have arbitrary metadata tags, and that's kind of where we get most of the value from, because we can attach whatever we want to each individual span. And distributed tracing in particular is special because not distributed tracing is kind of what you get if you just use the tracing library in your Rust program, and you can get this nested context as you can drill down into instrumented functions. And each time you call a new function that is instrumented, you attach additional span tags, and then, for example, in the middle log line, you get all those nested layers of context attached into that log line. But if you have several systems and you cross a boundary between one system and the other, you lose all that context. And, well, that's not good. So distributed tracing in particular holds onto that context even if you cross those system boundaries. So we know what all the context in a different system was, or maybe the system before that even. And you would then visualize that similar to this. So again, we have a trace down here, this time a different one. And at the top, we cannot see the actual flow. So on the left, we have the user clicking checkout, and it's a gateway and a front end, and then there's several services, there's a database, there's an external provider. But in the end, it all gets tied back together, and you see the different components, again, color-coded here, and you can see where we spend time. And you can't see the tags here, but they would also be there. So how do we keep this context? We can't send along all the span data, because that would be mostly eclipsing the actual payload you're sending across. So instead what we send along is just some identifiers, and we submit the span data individually from the different components. So if you look at this graphic I made, you can see we have a request coming to service A, it sends some span data to a collector, it sends some context, which is mostly IDs, to service B, and service B independently submits its span data. And because they both agreed on a trace ID, the collector can then stitch back together all the spans into one trace. And that's how you get the complete trace that spans several services. And you get a lot of info from that. When you get end-to-end visibility, you can easily identify where you might be spending time, where your system's slowing down. You can generate service maps. I can demo some of those later. You can track your deployments. And because of all the span tags, you kind of get like a debugger that you can just run in production at all times. It's not quite like a debugger because you can't request data quite on demand, but if you capture the data, it's going to be there. So if you're interested in a failing request or a slow request and you want to know what the request parameters were, for example, you can get that out of that. You can figure out which user it was, you can figure out where they were located. It's all there, assuming you captured it. And with that, let's get to section 2. So as I want, in this section we'll jump around a bit. So we will first start at the end actually, and we'll talk about how you actually get the trace data somewhere. So a common standard is OpenTelemetry, which is backed by the CNCF, and it's kind of a collection of different libraries, APIs, SDKs, and all of this is to work with different kinds of observability data. So it's platform agnostic in that there's many different libraries and it works kind of on free language or the platform. And it encompasses traces, logs, metrics, and even profiling. And it's using its own protocol, OTLP. But it depends a bit on which specific systems you're using, which are actually supported, which are quite compatible, and there's quite a bit of manual work involved to make it work. And while you're kind of also stuck in the shared standard, so you can't really get nicer, fancy vendor-specific features that maybe some observability platforms, especially paid ones, offer. So these are some commonly used tracing providers. We have Datadog, we have Honeycomb, we have Sentry, which are hosted paid options. We have Jaeger, Grafana, Kibana, which you can run yourself or probably also pay someone to run for you. And all of these do accept OpenTelemetry data. But we'll talk specifically about Datadog because that's what we use here at KOMOJU and what I personally think is the strongest product offering. So Datadog does similar to OpenTelemetry, all kinds of data, but it does even more than just OpenTelemetry, and it can correlate all that data together, which is really the unique value proposition. Datadog used an agent-based architecture, so similar to that collector I showed, or how you might have an OpenTelemetry collector. And you submit your trace data, among other things, to the agent, and the agent will then submit that data to Datadog themselves. And the agent can also be configured to pull data, so it can pull, for example, environment data from your cloud environment, so like running containers or things like that. It can reach into your SQL database and pull things from there. So it's pretty good. And Datadog have SDKs for basically all major platforms and languages, but not for Rust. And I don't know why, because I have Rust, but well. So I stole this graphic from the Datadog documentation. I hope you can kind of read this. But we have the environment, which is say like cloud environment, with the Datadog agent in blue. We have the runtime in pink, which is our application. And we have the Datadog API over here. And basically, we can get the agent off the shelf. It just have a container image for it. But we need to somehow figure out the pink bit if we want to be using Datadog to engage, for example, a service map like this. An important note here is you can't just keep all that data, because even in this model, this is a lot of data, and keeping it for prolonged periods of time at least is ridiculously expensive. So usually you end up sampling the data in some way. You might be sampling client-side, so directly in your implementation. You can set up the agent to sample as well, or you can sample on the Datadog side either ingestion or through retention filters. The caveat here is you want to make sure you get entire traces. So if you're doing client-side sampling, for example, you want to avoid service A keeping the spans for a trace, and then service B discarding the spans for the trace, and you have half a trace. That's not good. So there's some negotiation required to make that work. Notably, Datadog has 50-minute retention for all trace data at reasonable pricing. And they also can generate trace metrics from the trace data. And the trace metrics will come back later. They're very interesting. Basically, you can get things like request counts, error rates, latency distributions for arbitrary percentiles. So that's really useful if we're looking at, for example, request handling. So the way Datadog wants you to be using this is to not do any client-side sampling, just use the retention filters, get all the data for 15 minutes, and then only keep a section of it for say like a couple of weeks. The way to get the data to Datadog, there's two ways. So it can act as an OTLB collector, but you do need to configure it. You do need OpenTelemetry data. So if you don't already have OpenTelemetry data, you somehow need to generate it. And there's some mismatch in the data model between how OpenTelemetry works and how Datadog kind of wants to organize the code. So Datadog has a different kind of hierarchy where you have services which have operations which then have resources, and that doesn't exist in the same way in OpenTelemetry. So you kind of have to do a lot of manual tagging to get that to work. The alternative is use the Datadog-specific trace API, which the agent serves by default, and that's what all the cross-party SDKs use. And that's just message pack over HTTP on this port. There's a few different versions. And the agent is open source, so while the API isn't really documented, the agent is very well documented, so you can kind of reverse engineer from that and use the existing open source SDKs as implementation examples. Here are some versions of the trace API. This is not all of them, but there's 0.4, which is just an array of spans, basically. 0.5 introduced deduplication of strings, which is really good because in a trace you usually have a lot of the same tags, because everything has a service tag, for example, or an environment tag. So you can kind of deduplicate them and save some network traffic on that. And then recently they introduced a 1.0 version. It has more features, but none of them are really all that interesting as far as I can tell, because they're mostly advanced features that aren't easy to replicate outside of their SDK, at least so far. You can get protobufs for all these formats. The link here again. So the protobufs make it pretty easy to kind of produce the right kind of payload. Case in point, here's an example from 0.4 version. We have a Rust struct. You can basically chuck this into Soli as is for message pack. And if you sort it correctly by trace, you can send it to the Datadog agent on the port, and it will happily accept this. We can see that some of the important tags that Datadog really cares about are top-level fields in the struct, and the rest of the tags are sorted into these two hash maps, which are sorted into string values, number values, which I believe is a message pack implementation reason. And again, there's a link to the specific protobuf that replicates this. And next, let's talk about how we actually collect this trace data. So we know we want kind of what we just saw, but where do we get this from? So there's a few libraries I mentioned. There's no Rust SDK, but we have Tokyo tracing, which we all know and love. There's OpenTelemetry, the section of crates. There's also fast trace, which some of you might have heard about. And yeah, let's go over each of these. So tracing, we probably know, part of the Tokyo project. There's a lot of library support for tracing, so lots of crates have tracing features, so you can get more events automatically out of your crates. It has a really nice instrument macro that you can use to instrument your methods. And it has a very flexible output system where you can add several layers and subscribers to kind of like slice and dice the data how you want. And many existing subscribers in the ecosystem, so you can get all kinds of data out of it, like Chrome profiler or the Tokyo console. But so far, at least, there's no direct export to Datadog. And a small paper cut that annoys me personally, because I write a lot of libraries, is you need to declare all span tags for span and tracing upfront. So you can't dynamically add more tags to a span. And well, with all the tags we need, if you wanted to write a library, you can't just write a library that adds on all the tags, because you still need to declare them everywhere you use them. So you can have that problem that it leaks into your system. Next, the OpenTelemetry suite of libraries. So you can use them directly instead of tracing, so they also have an equivalent of an instrument macro. But you can also subscribe to the tracing data through tracing OpenTelemetry. And OpenTelemetry can actually export to Datadog in two ways. It can, of course, use OTLB, but there's also an OpenTelemetry Datadog crate, which you can use to use the trace API. The downside we have found is that you need to keep a lot of libraries in sync, mostly around the cluster of OpenTelemetry in supporting the system. So you're often blocked on updates, and you often get weird compilation errors when you try to update something, because you kind of need to update like a dozen libraries at the same time. And again, the data model between OpenTelemetry and Datadog, it doesn't really map all that well without a lot of bespoke tagging. So more work for us to actually make it nice to use. I want to briefly touch on fast trace. Fast trace is pretty new. It's supposedly much faster, like 100x faster or something than tracing. I don't know if that matters, but it's much more limited in features right now. You can also use it directly. You can also subscribe to tracing data. It can directly export to Datadog through fast trace Datadog, which is actually first party. But we tried it and we had a break in various ways. It kind of lost some data. It didn't tag data correctly, especially like in distributed contexts, and we even had some panics. So maybe not quite right for prime time yet. Next, let's talk about trace context propagation. So this is how we do the actual distributed tracing. So I briefly touched on this before. In distributed tracing, we need to somehow propagate the trace context. And in practice, this means we need the trace ID, the span ID, and the sampling decision, so we get an entire trace. And usually, you would use HTTP, because that's most protocols. And HTTP very conveniently has a side channel headers, so you can kind of like throw all your context in there. You can use middleware to inject it and then to extract it again. And it also works for everything that works over HTTP, like gRPC, GraphQL, message back. You have it. Protocols that don't have sidebans like this, like for example WebSockets, which are basically raw TCP, or even message queue hops, so like through RabbitMQ. Usually you need kind of in-band protocols where you inject the context and extract it again, but it's embedded in a message, so it's a bit more manual work. So when we talk about HTTP, there's four big kind of standards to use HTTP headers to inject trace context. Only the first two are really important, the W3C trace context and the Datadog specific headers. B3 has several variants. There's a single header and a multi-header version. It's coming from the OpenZipKit project, I believe. And there's also W3C baggage, which I haven't really seen used. So if we talk about the first two, we have the W3C trace context, which is really hard to say. And that has it has two headers and has this backlinked here. And we have the Datadog headers, which are actually just split up by all the different info. You see they're all X Datadog something headers. And again, we have the docs here, which actually just listen. It's like 5 or 6, I think. Realistically, you only need the W3C trace context, because even the Datadog SDKs, they produce it, they accept it, everything else produces and accepts it. So, and there's not really much extra info in the Datadog specific headers that we care about. I think you can transmit tags through them, but technically you can also do that through W3C. So zooming in on that, we see we have the trace parent header. And the trace parent header consists of 4 hex-encoded lowercase numbers. And we have a version, a trace ID, parent ID, and trace flags. There's actually only one version in the spec right now, which is version 1, I guess. The version number is 00. So this is just fixed for our purposes. There's also only one flag right now, which is it's bit masked. The flag is for whether you sample or not. And we already discussed we want to always sample client-side because we're going to sample later on Datadog. So this one's also fixed to just the value 1. The trace ID in this case is up to 128-bit, but to my knowledge, Datadog is currently only compatible to 64-bit, so you just leave the upper 64 bits zeroed out and it's fine. And we have an example here. The trace state header, it can hold extra information, but the spec actually says it's optional, so we just ignore it entirely. You don't need it. This is a long section, I think I give it. So, semantic conventions are kind of the bane of my existence over the last month or so. Datadog has a lot of span semantics, and it expects a lot of tags to be set to kind of like work the way they intended to work. There's an incomplete list here under this link, but it's incomplete. So, first of all, there is something called universal service tagging, which is the triplet of service and version, which kind of identifies a unique deployment. So that's on the highest level what everything's grouped by. Then also use the operation of the resource. So an operation might be something like HTTP request or message handled. And then the resource is like the specific endpoint or like the specific kind of message. So there's more hierarchy in there. It also uses span.kind tag, which is borrowed from OpenTelemetry. So that would be something like server or client or internal. And that has some implications when it comes to search indexing and also trace metric generation. Because, for example, you can only search for like service entry spans. So there's more tag semantics. So if you have inter-service calls, there's a special tag, peer.service, which marks a span as happening on one service, but also relating to another service. So it gets rendered as like A or B, basically. You can also use peer.hostname in case we don't actually really know about the other service, but you're kind of calling something that has a hostname. Errors have their own semantics. I have an example error here. I would have used a Rust error, but we didn't have any Rust errors, so this is a Ruby error. You can see this would be on a span. It has a stack trace, it has collapse, it has GitHub integration with code owners here. You can directly jump to the GitHub from here. It's pretty neat. HTTP requests, of course, have their own semantics. There are a lot of HTTP.something tags like status, method, etc. Database queries have their own semantics, and we'll see a bit more of that in a little bit. And there's also some secret span tags which Datadog don't want you to know about, but are essential. So there's the underscore DD top level tag, which is it's a numerical tag. It would be 1. And it would mark service entry spans. And as I mentioned, service entry spans kind of like special spaces in Datadog. There's also the underscore DD measure tag, which enables trace metric calculations. So that's how you get all the error rates, the latency percentiles. You do want to control that separately because I believe you end up paying for those. So you don't just want metrics generated everything because it's going to cost you. There's more of these, like there's one for the upper 64 bits of 128-bit trace IDs if you have 128-bit trace IDs in your system, but I mean, Datadog ignores the other 64 bits, but maybe you still want to pass them on later. And so there's a few more on this like sample rate thingy. I haven't been able to find a complete list of the _DD ones. You kind of just have to look at a lot of the SDKs and the agent code to kind of reverse engineer this. So one of the things all the tagging gets us is correlation. And I mentioned the competitive advantage, in my opinion, of Datadog is they can correlate a lot of data. So if we have a lot of data coming from different sources, maybe, some submitted explicitly to the agent, some collected through the agent, some may be actually coming from somewhere else, Datadog can kind of put all that data back together. So we've seen, for example, the error, it had info from GitHub, namely like the source code links, but we still have that in our tracing info. And the solution for that is basically we have to pass trace and span IDs everywhere, so that whatever else we emit the data, we can then link back to that. And well, that means more semantic conventions of where we put those IDs and how. The first one's logging. It's probably the most popular, and everyone has logs. And if you want to be able to see the logs for a specific trace, or the other way around, you have a log line and you want to find the trace for it, you tag the log in the correct way, Datadog does it automatically, and you can just look at it. Generally in Datadog, you log to standard out, depending on the platform, and there's a JSON format that they also haven't really implemented. But it has a message field, it has some fields for span and trace IDs, and you chuck all the other fields into fields.fieldName, and then it works. It's kind of different enough from tracing subscribers JSON output, so that you can't just use that. But there is this library here that does that as a tracing layer, but it also does it using OpenTelemetry, so you can pull in a few extra libraries just for that, which I think is a bit heavy-handed. Next we have database queries. We have here again an example database query from actually our production system. And you can imagine this attached to a span directly, which would track that database query. So you can kind of get inline stats, you can get like the whole query text, you can see like the number of reads and rows written, there's more stuff you can get out of there. You can even get explain charts, which the database can collect depending on settings, and then the agent pulls from the database using like the performance schema. And yeah, if you then have the right semantic tagging on your tags, on your spans, so you include, for example, the database statement, which is like the whole SQL text, you get the nice rendering. And if you want the whole linking, you also need to pass all your trace and span IDs into the query, which you do through a magic comment format. So you prefix all your queries with a comment that has basically, it looks like log format, so it's like foo equals bar. And then has all the trace and span IDs, and then you can correlate it back. Again, you can also go from the other side, you can like, look at the database metrics, you can see all the queries that are running, you can see which queries are slow, and then you can click back from there into the tracing data and see, okay, what are the requests that triggered those queries. So it's really handy that way. When your database is locked down, you're not sure what traffic is causing that. You can also get infrastructure metrics. So these again are collected directly from the agent from the cloud environment. In our case, this is now AWS, ECS. So you can get, for example, CPU and memory, you can get I/O, you can get, I think, like 8 more or so. And if you tag your tracing data with the container ID, again, this data will show up right in line in your trace. So you can see here's the red line for when the trace happened. So if you have a trace that behaves kind of abnormally, and you want to see if that correlates to any kind of like system resource event, it would be right there. Weirdly enough, there's no span tag for that correlation, but instead the trace API accepts a special header. So you just need to send it along the data container at HTTP header as you submit your trace data, and then it will do the linking. And with that, we've made it to part 3, and this is kind of where we tie it all together. As I mentioned. So the common stack is use tracing to get kind of like the nice UX or developer experience we all like. You then use tracing OpenTelemetry to get all the data over into OpenTelemetry, and then you use probably OpenTelemetry Datadog to submit the data through the trace API to Datadog. You then also use the data formatting layer, which I linked, to kind of get the log formatting. You add some more supporting libraries, you end up like 12, 15 or so in total, and you write maybe a couple hundred lines of code to like, do all the tagging you need. And yeah, I think that's not fantastic. We have a lot of pain points here. You need a lot of code to get all the trace data. I mean, you need 100 lines of code just to get trace data at all. I've measured it, it's like 97 or so. And you need a couple hundred to maybe 1,000 or so to get it like formatted like it looks first party. So that's a lot of code. You also need, I think the minimum is 7. Like I said, you might end up about twice that libraries that you need to keep in sync. And you can easily get stuck on updates because some of them aren't sort of maintained. If you break them, sometimes you get compiler errors because well, different crate versions produce different types, even if they have the same name. In some cases, it works, but you just lose the trace data and you find out when you deploy to production. Ask me how I know. And also, again, my personal paper cut, having to declare the tracing span tags upfront, it means every instrument call you have goes with like 10, 15 span tags. So everyone in your system needs to include those span tags. Those semantics going to leak everywhere, and you know, if you're trying to have a nice creative experience where you don't really have to care that much about your instrumentation system, that's not great. So I figured we can do better, and I think we did. So I mentioned I work on internal libraries. I wrote an internal library. I wrote kind of like the a mini Rust data SDK, and it does a lot of stuff, but it allows you to kind of set up all your tracing setup in like pipelines or so. After that, you get to use tracing as you normally would, like no special tags for the most part. 90% less special tags. You don't get any dependency on OpenTelemetry, so you don't have all the like, keeping the library in sync pain, and also it's a lot of libraries. Who wants libraries? You get the trace data export directly into Datadog using the trace API that we saw. You get the logging in the right format. It does have the correlation to the trace data automatically. Because we use Axum, and this is an opinionated library, it has a middleware for Axum, so it automatically creates the request spans. It extracts the trace contacts from the headers. It does a lot of the semantic mapping automatically, so it tries to be smart about like which tags you need to attach so that it shows up correctly. And it has like 10 more features that I couldn't fit onto the slide because every time you type, like the font gets smaller. But I have a list here in my speaker notes. It has support for ECS, it has support for SQL queries, it has HTTP header injection, and even more stuff. And well, if this doesn't sell you on it, then I also don't know. This is the entire setup actually from our system. So you see, we define a service name, we define an environment, we define a version, and then we just, okay, start tracing. And yeah, that's how you get tracing. There's a few spin-off components. So I mentioned it's quite opinionated. Like right now it supports specifically ECS because we use that. So if you're not a fan of that, we do have tracing Datadog separately, which is just the tracing subscriber. So it gives you all the like trace submission, it gets you the log formatting, it gets you the HTTP trace contacts handling, but it doesn't do anything else. So like all the tagging and everything is up to you. You can craft a different developer experience. We also have SQLX Datadog, which does the SQL bit, because again, we use SQLX. So there's a different instrument micro, which is instrument query, so it attaches all the right kind of tags to make the query look like the example we had. But that one's still a bit work in progress, so it works for us, but it's still a bit janky. And it doesn't do the trace context comment injection yet, mostly because kind of it's a proc macro, and my proc macro skills are not that great. But yeah, you can check this out. It's all open source. I've linked them here. We have KOMOJU Datadog, and all the other two are my personal projects. So put them into my personal GitHub so I can get more stars. But yeah, you can send us changes. It's all MIT, so you can fork it as well. You can steal the code, use it yourself, and you can also just pull it off Quixo if you want to use it as it is. And yeah, so that is actually everything I have. I was passing it. I have another slide that's for questions, but I got asked to maybe showcase Datadog a bit, just to like really sell why we think it's great. So I will take a minute to just show what Datadog actually looks like for us. So I have in the next tab over here. So this is set service. This is currently running production, and you can kind of see what you see, for example, on the service dashboard, which is representative. We have requests, we have no errors, which is very good. We have some latency distribution here. We see there's a P99. We currently have no deployments because I'm not currently shipping, I'm talking. You can see here, which I think is very cool, you can see the time spent per request by component, and that extends to third-party components. So you see this like 33 milliseconds is spent on a service called Hats, which is ours, calling a Steam API, who are one of our partners. And if that were to spike, we could directly pinpoint that, oh, looks like Steam's having a bad time. So, not our problem, but maybe we'll talk to that. You can see here a list of endpoints, like this is our API. If you've seen our API docs at some point, you might be familiar. We can see requests and latencies and error rates and all that good stuff. I could click into here now to get more details. With deployments, again, there's no deployment, last deployed a day ago, currently. I mentioned we get service maps. You can see we have automatically generated service maps. Like this is parts of our system. You can hover over that, and you can see how much traffic is coming from where, how it's behaving. You see there's a view traces link. You can directly look at traces coming from this service to the other service. If I can scroll, here we have some infrastructure metrics. You can see we have here the summary, this network traffic, memory usage, and then last but not least we have the actual traces. So here you can see every single request, and no errors. There are few logs, and then there's more stuff we don't really use. But yeah, so that is an example for what you get out of Datadog, and that is kind of the highest level overview. And yeah, I hope that sets you on this. With that, I'll flip back to questions, and one of you has questions. I will also at this point flip forward to this. So I've got the slides. This is a QR code with the same link. There are some other interesting links. So if you want to get the slides, get the links that are in the slides, which might be more interesting. There you go.
Have you seen any of our videos?
No.
On YouTube? So you don't know what's coming?
I'm not going to have a bad time.
No, we're going to have a great time. I'm just going to ask you some questions about Rust. Maybe first, how did you get into programming, working with computers?
Video games. Yeah, I was like 12, 13, and I wanted to make video games because I like video games. So I started learning C++, and I didn't have a great time because if you're 12, 13, learning C++, it's not what you should be doing. So I still don't know C++.
The designer of C++ is quoted saying he knows about 70%. So don't feel bad. Which video games did you play that inspired you?
I played a lot of party games like Warcraft 3, Age of Empires, Counter-Strike, and then I lost a few years of my life to World of Warcraft. I was in a top 10 world rating bid at some point.
All right. So C++ was your first language, you said?
Sort of. I mean, my first serious language, I think, was C#. And then my first professional language was Python.
What language did you use before learning Rust? Was it Python?
No, immediately. So here at KOMOJU, lots of Ruby, of course. Before that, mostly Clojure. Also some Go, also some Rust. Before that, Python and Elixir. Before that, Haskell. Long list. I've done like half the languages out there.
It sounds like you know a lot of languages, so it was probably easier for you to wrap your head around Rust. What would you say was the most difficult part?
I was recently thinking about this because we have a lot of Ruby developers at KOMOJU who are thinking about learning Rust, and I've been thinking about whether the learning experience or the learning curve is actually as steep as everyone makes it out to be. I can't really remember learning it. I think I bounced off Rust once or twice before I actually ended up committing to learning it. So at least back at the time in like 2019-ish, it was pretty hard. But yeah, maybe it's better now.
Can you think of some advice that you would give somebody who's just starting to learn Rust? What is something that could make their life easier?
Don't always try to do it the right way, just get it working. I think there's a lot of purists in the community. I think there's things like, if you need to clone everywhere, if you need to unwrap everywhere, just do that. And then I think there's kind of like a more natural gradual learning curve where you start doing sync Rust and then async Rust, and then maybe at some point you dabble in Mac Rust. I think then it's not too bad, but if you just jump in right into the hardest bits, you're like, oh yeah, I'm going to like properly plan Mac Rust, then I don't think you're going to have a good time.
Sounds very sound advice to me. Do you remember what your first project was with Rust?
I recently looked at it because it's still on GitHub. I can't remember when this. I might have written a text adventure. I often write text adventures because they're easy.
Text adventure. That sounds familiar. I think we had somebody visit our community from, he lives in Fukuoka, maybe. This person works on a text adventure game using LLMs in Rust.
Yeah, I mean, I think Rust is a public language for text adventures. I've never finished one. I've got like 24 half-finished text adventures.
My last question is, what would be a project or presentation topic that you would like to see here?
I mean, we chatted about this a bit before. I have a hard time wrapping my head around Web. I think maybe someone just talks about it for an hour and that might help me. So yeah, that might be a good idea.
Which part? Do you mean something specific like the ECS or just a game engine in general?
I think both. I don't really have a game background, despite my aspirations. I at some point learned that the games industry is not really nice. So I ended up in web mostly. But yeah, I don't quite understand ECS, and also otherwise I don't really have much context about what actually makes a good game engine. So yeah, I'm sure there are plenty of opinions on that.
I think that's a great topic. I hope you all are taking notes. I would also love to hear about Debbie. Thank you, Robin. This was a great presentation.
Q&A? Yes, please.
Yeah, thank you for a very interesting talk. I just wondered, did you consider efficiency from the size point of view? You mentioned like a dozen of different headers, and it seems if you make your trace detailed enough, your service will only be working to deliver traces.
So this is why we don't actually include all the trace data in the headers, but we only include IDs, so it's like fixed overhead. So you only need that one W3C trace context header, which is what fixed couple of bytes, I guess. And well, otherwise you're submitting all the data separately, so you usually do it off thread somewhere. So You submit all the data somewhere to a buffer, and then you have a separate thread that then submits them away, so you don't block your main thread.
Yeah, I'm not talking about the blocking, but it's just interesting, the volume of data used for service and volume of data used for tracing. I think it's like comparable.
Yeah, you're probably not wrong. There's probably a lot of data going through it. At least for us in reality, like network throughput is not the bottleneck at all, so it doesn't really matter. And again, we've seen with the 0.5 trace API, there's a lot of compression going on, and I mean, message pack is a bit more efficient than just sending like JSON, for example. And I don't actually know if there might also be transport compression because of HTTP, so you might end up getting some gzip advantages there too. So for us, it's not noticeable, and I mean, the gain far outweighs the cost.
Yeah, okay, thank you.
Hello, similar question. Do you have a ballpark idea of what the overhead of the tracing library is? Like, how long does it take to start a span, create an event? Like, if you list instrumentation everywhere.
Yeah, so the fast trace library has a graph to kind of sell themselves. And like I said, they claim something like 100x cluster or so, but all of that is usually measured in microseconds. So in situations where you're doing HTTP calls and SQL queries, it's negligible.
Thank you, Robin. I really learned a lot. My impression is the tracing library, Tokyo Tracing, is mainly producing logs, like different levels, warnings, errors, those trace macros. So I'm wondering how does that information get sent to Datadog via KOMOJU Datadog? Is it also being subscribed via certain?
Yeah, so tracing kind of conflates the two. Tracing has traces and spans, and the logs and tracing are actually events, and they're like automatically already linked in tracing. And so all the traces get exported through the API I just showcased, and the logs get exported through, in our case, it's over standard out in that specific JSON format, and then I think we use Fluentd to pick them up, but that then depends on like, are you running on a cloud or bare metal or like which environment. But yeah, both of those go through the tracing subscriber because tracing kind of handles both of them.
I see. How is the level filtered? Is there a configuration?
Yes, so traces also have the same levels, and you can use them to filter them. So you can have info spans or error spans as well. I don't think we use them, we just use info spans for everything because we don't really want to filter the spans as I mentioned. So we just get all of them. But for log lines, for example, we would use the levels to filter.
It's a global one.
I mean, technically you could write a bespoke filter that filters more specifically, but yeah, generally you just select a log level and just say, give me like up to info or up to debug.
Got it, thanks.
I was kind of wondering about you're saying earlier you had a whole bunch of libraries with the one telemetry that all had to be kept in sync. And I'm wondering what factors made it such that you couldn't, like, for example, just peg a version, right? Like, is it security problems? Is it something else? Or
I mean, you could, but well, then you're not getting updates. Presumably there's something in the updates you want.
okay, so you wanted to make sure you were with the latest version.
Yeah, I mean, tracing itself doesn't really move that much, and I think OpenTelemetry does a bit, but some of the other libraries maybe that also depend on tracing then might move, and they might implicitly, as part of their version bumps, also upgrade tracing, and then you're forced to upgrade tracing, and then you're forced to upgrade OpenTelemetry, and then everything works. So yeah, I think generally being stuck on an old version of anything is not a good place to be in.
Yeah, so yes, I wonder how you decide what do you want to track, so which span, and it's useful for every method. So how do you decide where do you span and track?
Yeah, so I mean, definitely not every single functional method. So we generally do kind of service entry points, so like request handlers. We do any service exit points, so like queries, external HTTP calls, And then anything that either could take significant amounts of time. So we, for example, we have password hashing at some point for like comparison. So you might want to keep track of like how is the password hashing latency developing, or anything where you might think there might be interesting tags that you might not want to declare on higher level span. So if there's like some operation happening where there's like tagging info you might want to keep, like I don't know which customer it is, or like the outcome of some kind of decision. Like mentioned over here's work on anti-fraud systems, you might want to track a whole bunch of information on like decision making to anti-fraud for anti-fraud purposes. And that doesn't make sense on a request span, but instead on some kind of like decision function.
Thank you for your nice presentation. I'm interested to see the GitHub project. I was wondering, what I felt is in the absence of Datadog providing the SDK for us, so you basically reverse engineered and have come up with an open source this. So thank you for that community work. How would you feel do you feel like feature complete wise? Like, let's say one day Datadog comes with the Rust library, so how would you compare it to the current version? If somebody committed to, let's say, using KOMOJU Datadog, do you have any points where okay, I need to implement these features or feature complete as well?
Yeah, so we currently cover kind of the essentials. So, like I said, we have tracing, we have logging, we actually have metrics, which I didn't talk about at all, but Datadog does metrics through StatsD. We have StatsD supporting that too. We have something called span links, where you can link spans outside of a parent-child relationship. But there's parts we don't have, for example, profiling, because that requires, I think, a lot of work. I haven't really looked into it yet. So it's you actually need to collect effectively profiling data like we would do for a frame graph, and then submit that somehow. So some of the advanced features are definitely still missing, and I don't know if they're worth the effort at this point.
Yeah, thank you.
But I mean, if you want to submit some additional functionality.
So this is just curiosity. I saw on an earlier slide, Datadog had a link, and I've seen this acronym before, something like APN. And I was curious if you could fill in, what is APN and how does it relate to tracing? Are they the same thing?
It's application performance monitoring. It's their name for the tracing product. So it's all the tracing info, and the maps, the histograms, etc.
Does that include you mentioned briefly that there's metrics supporting tracing? Does that include
No, the metrics are separate. I think they did metrics before they did tracing, if I remember correctly, many years ago. So they're also kind of separated in the products. There's not a lot of good integration between metrics and tracing.
And one more thing, and you said that Datadog supports metrics, and that they probably supported that first. Does Tokyo Tracing support metrics as well? Can you aggregate metric data like this method was called so many times kind of thing?
So you can through the trace metrics, but the trace metrics are generated by Datadog from the trace data. So that is the _ed measure tag that I showed. So it will get call count, error rate, latency, percentiles, that kind of thing. Otherwise, the generic metrics, so you can submit counters, distributions, sets, and a few other types. Those are all StatsD. They're entirely separate thing, and tracing, to my knowledge, does not support those kinds of metrics. But yeah, I think OpenTelemetry has something like metrics. So you could technically pull them in from there, but we just use StatsD directly. So you just declare, say, a counter, and you say, okay, increment this number by some number.
Okay, thank you. You mentioned that the tracing data is sampled. What is the rule for the sampling? Is it sampled as a fixed rate? And where does the sampling take place?
So the way we use it and the way Datadog, I think, want you to use it is there's no client-side sampling in your service. There's no sampling in the agent, but you send everything to Datadog, and they keep everything for 15 minutes as a rolling time window. And then after that, there's retention filters. You can define custom retention filters, like you might want to keep everything that has an important customer or something. But otherwise, their default filters, they have they keep everything that's errored, so you get all the errors, and then they kind of keep like a smattering of all the different resources, so like endpoints, for example, so that you don't just get 98% like health check traces, and then like that endpoint that's called twice a day isn't present at all. But they have, I think they call it diversity sampling, so they try to keep everything kind of included to some amount.
Okay, thank you. Thank you for your presentation. So the earlier presentation, earlier page in your presentation, you told about so to keep the context, maintain the context, we need a collector service. So can it be so in the distributed system? So can it be a collector? Can it be a bottleneck or some single failure point to collect? So all the context information goes to that collector.
Yes, you're right, it could be, but you don't actually need a single collector. So the whole stitching together part in the Datadog case actually happens on the Datadog server side. So what we do and what they kind of advise for our setup is, per service we run a sidecar agent. So for each service container we run, we have an agent container, and we actually just submit the data to localhost because it's like in the same pod or something.
Mm-hmm. Okay, so the collectors are also kind of distributed.
Yes. So it doesn't matter which collector you submit to. You can run like a pool of collectors that you might auto-scale based on traffic, or you might run like one collector per service, or you might run a single collector if that's enough for you and cheaper. Yeah.
Thank you.
So does Datadog do comparative metrics? Like, say you do a release and you want to see how the distribution of the latencies compares before and after.
Yes.
Is it good at that?
Yes, it does that. If I go back here, scroll, if I can find the cursor, if I scroll all the way back up, and you can see this is actually request for versions and latency by version. You can like select a few different kind of things here. You can see like historical. But if I were to, I'm attempting the left, of course. Zoom out here to a week. You can see how the color here changes between the different versions. So you can see if one of them goes like way up or way down. It also has a bunch of smarts. So if a release increases error rates or latency, it has a thing called watchdog. So it will automatically, if you actually then goes, oh, I suspect there's something bad with that release, you might want to have a look. I mean, we have that just hooked up to Spark, so you can just see it's like something's up. Okay, cool, thanks.
It seems like this is quite a bit of an undertaking, but tracing is important, so it's very likely that the larger community would benefit from kind of like a one-stop shop solution.
Yeah, I do believe so. I think so far it has been, I mean, I think lots of people aren't really all that familiar with tracing and why you might be interested, so I've tried to kind of show the value proposition, and then even then it has been a bit of a pain to set up. So we came from the Ruby side, we already had Datadog set up, and we were like, we need the same thing for Rust, and well, there was no good solution, so we had to come up with one.
Have you considered applying to the Rust Foundation for a project grant?
No, the thing is, I mean, I have a full-time job, I'm not sure if it's I mean, I would gladly take money, but then I would feel obligated to actually put time into it, and well, I have other lives outside typing into a computer.
Makes sense. Thank you very much. We'll wrap up here.